We had previously seen that when we use a composite structure or a hybrid, then we can get beneficial properties which are neither found in neither the one of the components which go on to make the hybrid or the composite. Additionally, we had seen that how a polycrystalline material can be thought of as a composite of grain boundaries, the crystal, the triple line junctions and quadruple junctions, and we had also made a calculation on the upper bound and lower bound on the elastic modulus when we use this concept to understand polycrystalline materials, especially at the nanoscale. We had also seen the relationship known as the Hall-Petch relationship, in which we had described the increase in yield stress with decreasing grain size, and we had seen that the relationship, if you plot sigma y versus d power minus half, then you will find a linear relationship. We had also pointed out that it is actually the grain boundaries which are responsible for such a relationship, and one of the common models used to understand this Hall-Petch effect is known as the dislocation pile-up model. We had also noted in that context that actually that this model, though it is a popular model, that often electron microscopic evidence is not available in support of this model, even though this kind of a behavior is seen in a wide class of materials across large variations in grain size. But we had also noted that when we go down to very small grain sizes, actually the Hall-Petch relationship breaks down, which is what is expected, and we noted that there could be a regime in below about 20 nanometer grain size, wherein you could have an altered strengthening, but with decreasing grain size. We could have a no strengthening with decreasing grain size, or we could also have what you might call an inverse Hall-Petch effect, which is a absolutely new concept, which is coming basically in the grain size being in the below about 20 nanometer, which is especially new for nanocrystalline materials. Now, we will consider an hybrid, and we will also explore the possibility of the applicability of Hall-Petch relationship in nanolaminates and particulate composites. Nanolaminates are hybrids with layer spacing of a few nanometer. A schematic is shown below, in which you have two materials, and in the example considered, one material could be nickel, another material could be copper. Of course, you could take a wide variety of materials. For instance, you could have a germanium layer followed by a germanium silicon solid solution layer. You could have a gallium arsenide layer and an indium gallium arsenide layer, but anyhow you can form a bilayer, which is basically a 2D nano crystal, and you can stack them one on top of the other to obtain a laminate structure. The two layers could actually be coherent with each other, they may be incoherent, or they could also be semi coherent, and in the process you actually have a long periodicity, or you have a periodicity in the z direction. So, this is my z direction. The important point to note is that, of course, this is my layer period, that is, this is my unit cell parameter along the z direction. Now, this implies there are two length scales in this problem. One length scale is related to the lattice parameters of each one of these crystals, and suppose I am talking about nickel and copper, then the lattice parameters of the individual components is one length scale in the problem. The second length scale is, of course, the individual layer periods, and if I take them to be equal, then I need to talk about the periodicity along the z direction, which I just described, which is an additional lattice parameter in the structure. Now, such a structure can be called a super lattice, because now, and it is a super lattice in the z direction and the reason that you tend to form such kind of composites is because you get additional benefits which are not found in either one of those individual components. Now, in the case of nickel and copper, if I make a nano laminate, that means the periodicity is of the order of 10s or 20 or 30 nanometers, then it is found that the nano laminate formed from two soft metals like nickel and copper. Nickel and copper both are FCC, that implies that the Pearl stress in these structures is small and they easily plastically deform. Then this nano laminated can have a strength of the order of a few GPa. That means we are approaching the theoretical shear strength, which is of the order of g by 2 pi in nano laminates. This is a very beautiful and strange effect. That means that we are getting very high strengths in these nano laminates, while each one of those components, nickel and copper, actually are very soft metals. In titanium nitride, niobium nitride multilayers, that means one layer is titanium nitride, the other layer is niobium nitride, we can have a hardness value approaching that of about 50 GPa. And if you note the hardness of individual layers like the titanium nitride and niobium nitride, that is much lesser than this value of 50 GPa. The important point to note in this context is that not only are we getting this kind of a hardening effect, but suppose I study the hardening effect as a function of the bilayer period, and for now I assume that the individual layers made up of either titanium nitride or niobium nitride, or in the nickel copper system either made of nickel and copper, are equal thickness. I do not vary that thickness, I keep it constant, but then I vary the overall periodicity or the layer thickness. Then if I plot a log of the bilayer period versus the tensile strength, and often in such systems either you measure the tensile strength or you may even measure the hardness, then you find an approximately linear relationship with a plot showing a slope of about minus 0.5. This is like a Hall patch behavior. That means that now if I am plotting log bilayer period versus the log of the tensile strength, I find an approximately linear plot which shows a slope of minus 0.5, which means that we are seeing an effect which is very similar to the Hall patch effect. That means that in the Hall patch relationship, we originally pointed out that typically we plot yield stress, and yield stress follows this relationship. We had extended to say that even hardness follows this relationship. Now we are saying not only is the grain size d which follows this relationship, but could actually be a bilayer period in a nanolaminate or in a laminate structure. So this is a very interesting effect, and if you dwell a little deeper about this nickel copper superlattices, you would notice that in a decreasing bilayer period up to about 20 nanometer leads to an increase in the yield stress in the tension test. Further decrease in bilayer period leads to a decrease in the strength. The peak strength corresponds to about 1 dislocation per layer. So this linear trend is of course followed in a certain regime, as I pointed out, and would not be followed in a very large period. But the interesting thing is that the peak strength corresponds to about 1 dislocation per layer, and of course we will soon see what is the mechanism which has been attributed to this kind of a strengthening. To summarize this slide, we can not only have nanoscale materials, but we can have nano hybrids, in which case the two components forming the composite or the hybrid structure are of both of the nanoscale. In this case, the individual layers, for instance, of nickel and copper are on the nanoscale, and not only that, this kind of a nano laminate actually shows very high strength, even though it may be made of materials which are actually soft like nickel and copper, and this can approach almost the theoretical shear strength of the material, and that means the yield stress could be of the order of gigapascals. And additionally, you also observe Hall patch kind of a behavior in a certain grain size or a bilayer period regime. Now, the hardening in such multi-layers and superlattices have been explained using a number of concepts. We just list them here, we do not go into the details of some of these, because some of these are still debated upon which is the correct mechanism, which is the dominant mechanism in one kind of a system vis-a-vis correct kind of mechanism in other system. But some of these we list here, and we may make a few additional comments. They are talking about increase in barrier strengthening, which is giving rise to this kind of an extraordinary strength in the nanoscale. There is expected to be some kind of a coherency between the two layers. Suppose I am talking about two layers, this is my layer A and this is my layer B. So it is expected that this interface between layer A and layer B could be an coherent interface. That means there is an epitaxial relationship between this A and B layers, and which gives rise to certain coherency stresses, and these coherency stresses are going to modify your local stress state, which is coming from an externally applied shear stress or a tensile stress. It is also assumed that if this bilayer period becomes large, and if you start with what you might call a coherent system, then it will no longer remain coherent for large thickness, and in fact you may obtain misfit dislocations decorating the interface. So typically you could have certain decoration of misfit dislocation along the interfaces, which implies that the system is partially coherent, and this misfit dislocation would impede the motion, and this misfit dislocation, as we have noted before, is a structural dislocation. It is not a statistically stored dislocation in the bulk of the crystal, and such a misfit dislocation would tend to give rise to certain hardening effect, which is seen, which could attribute to the additional hardness of such a material in the nanoscale. Additionally, there is the concept of the dislocation image force, which we have encountered before, and this is due to the discontinuity in the elastic modulus at the interfaces. A few words may be necessary here, because this is not the classical image force, because in the classical image force we have noted before that you have a free surface and there is a force which is attractive force towards the free surface. Now, we can extend this concept of an image force. In this case, of course, I can make a image construction, and therefore, the attractive force between the two is called the image force, but I can extend this and this kind of a force is called a configurational force, because this is coming not because of an individual mass particle being attracted to an individual mass particle, but because of the configuration of the entire system. And such a configurational force can also exist between, for instance, a harder material and a softer material. And if I put a dislocation in a harder material, it will be attracted towards the softer material, and this is I am talking about elastically harder or softer. So, if I have harder material and the dislocation sits in the harder material and there is an interface with a softer material, then the dislocation may feel a force towards the softer material, and this kind of a configurational force can of course loosely be called an image force, even though we should understand that actually now I cannot have an image construction, because this is not valid anymore, this is not a free surface, this is a softer material. Nevertheless, the dislocation will feel a configurational force towards a softer interface, because now the energy of the system would tend to decrease as the dislocation is positioned closer and closer to the softer material. That means that such kind of effects also seem to play an important role in the strengthening of these bilayers, and they have also been attributed to give some effect, some additional effect to the hardening, which is seen in these bilayers, which we have seen approaches the almost the theoretical shear strength of the material. And additionally, of course, some common mechanisms which are observed in the case of large grain size materials like dislocation pileup and bowing of dislocation, which is like the Orawan bowing, are also observed, but now we have to note that this can only occur at larger bilayer periods. That means that in smaller bilayer periods, we already noted that there is not enough space for a mechanism like a Frank-Reed mechanism or a Orawan bowing mechanism to operate, and we have already seen that when you talk about a really small periodicity, then the whole region can only support only one dislocation per layer. That means that it is not possible to produce, put multiple dislocations. Of course, when I am talking about multiple dislocations, I am talking in the thickness direction. So, there could be of course many dislocations in the, and of course, I am schematically showing here in the direction of the x or y, but in the z direction, which is perpendicular or the direction of the periodicity of the laminate, you do not expect more than one dislocation, and of course, you could have even smaller sizes when the system becomes completely dislocation free. In other words, no dislocations are supported in the bulk of the two crystals which make up the superlattice. So, we see that in nanolaminates we can obtain very high strength, and this is to understand this, when we have to invoke a mechanism which is now thickness dependent, it is not independent of thickness, and therefore, if you go from larger bilayer periods to smaller bilayer periods, the mechanism may switch to a normal what you call dislocation pileup or a bowing mechanism to other kind of mechanisms which are operative, like we just now saw the image force mechanisms, etc., at very small bilayer periods. Like we make a nano composite between as a laminate composite, we can also make nano composites the usual way, which is the particulate nano composites. And herein also we have of course we see a lot of beneficial effects of putting nanoparticles in a bulk matrix. That means the relevant nano entity in this whole system is the reinforcement. That means I could actually have a polycrystalline material, and the grain size of this polycrystalline material is could be in the micron scale or tens or even hundreds of microns. That means this is not the relevant nanoscale dimension, but then I could put particles inside here which are used as reinforcement, and for now I will draw schematically these particles as spherical particles, though there is no reason to believe they have to be spherical, and these particles could also be precipitates. And this nanoscale dispersion of the second phase in a bulk first phase can actually give rise to a tremendous increase in strength, as shown in some of these examples here. We have already of course talked in detail about the precipitation hardening system, wherein you have precipitates of the scale of 1 to about 100 nanometers, and we will not repeat it here, but which is the case of the duralumin, which is a precipitation hardening system. But we will take up other examples like nano sized molybdenum in a volume fraction about 5 to 20%, which is from the usual small volume fraction to a reasonable volume fraction. When it is dispersed in a micrometer grain sized alumina, that means the grain size of alumina is no longer the nanoscale, it is only the molybdenum reinforcement which is in the nanoscale. There is considerable improvement in hardness, fracture strength and toughness. So, you see that the properties are overall enhanced by putting a nano sized molybdenum in a alumina, which and you know that alumina is a ceramic, that means that it is prone to brittle fracture and its fracture toughness is expected to be small. Therefore, there is a tremendous reason to add these kind of particles which will give you an increase in fracture strength and also in the increase in toughness, and toughness being the energy absorbed before fracture takes place. Nano size silicon carbide dispersions, again we are talking about silicon carbide in the nanoscale of about 200 nanometers in the same matrix, which is the alumina matrix, also leads to an increase in fracture strength by a factor of 3. So, this is very important, because alumina, as you know, is being a ceramic, being an oxide, it is in a stable state. So, it is prone to it is resistant to some of those usual things which metals are not resistant, like corrosion, etc., and it has a good elastic modulus as well. But the problem with ceramics, as you know, they are very intolerant to cracks. In other words, they have a poor fracture toughness. So, by adding silicon carbide dispersions in the nanoscale, you can get a increase in strength factor of about fracture strength of about factor of 3, which is a pretty good increase. The high temperature mechanical properties are also pretty good, and you know, typically these ceramics do find applications in high temperature, and this would be a good thing to add actually silicon carbide. The decrease in hardness with increasing temperature, which is what you expect, because now you can have thermally activated motion of dislocations. In other words, in normal alumina at room temperature, the strength is very high because dislocations are not that glissile, the Pearl stress is very large. But then when you go to high temperature, some of these will start showing plasticity, because now you can have thermally activated slip, and also other mechanisms like grain boundary sliding may start to take place, and therefore, this softening effect is significantly reduced when you use an alumina silicon carbide composite rather than a monolithic alumina. That means, you have benefits on all fronts, you have benefit in the fracture toughness, you have benefits in the high temperature strength, and also in the case of molybdenum in alumina, you actually have an increase in hardness and toughness also. Therefore, it makes sense now to actually make some of these composites with reinforcements in the nanoscale, and we have already seen one example wherein carbon nanotubes has been used for reinforcement of alumina, and we have seen that typically these are multi-volt carbon nanotubes, and by doing so you can actually get a benefit in strength there as well. So, to summarize these slides, we have of course individual nanostructures which themselves show very good properties, but then we also have composites and hybrids wherein at least one relevant entity is in the nanoscale, which can also give us improvement in the properties. Next, we take up the issue of creep in nanomaterials. We had earlier talked about creep as a general phenomena, and we had also talked about various kind of creep mechanisms, and we had talked about issues which will be highlighted when we go down to the nanoscale. We said that some of these mechanisms of creep, for instance, when we talk about these diffusional mechanisms, when we talk about issues like climb, we said that when you go to nanoscale, all these effects will be enhanced, and therefore, you would expect certain what you call creep rates to be high. Additionally, we also noted one of the important mechanisms of creep is this grain boundary sliding, and if you go down to and we noted that for grain boundary sliding, in some sense we have to cross the equicohesive temperature. Decreasing the grain size in some sense is like increasing the temperature, and therefore, even at low temperature we said we would expect some kind of a what you might call a behavior like a increased creep rate. That means, we noted that we would expect in nanostructures, in nanomaterials, high creep rates, and that too at lower temperature. So, this is what we had expected, we had anticipated. Now, we will actually see how much of this is actually true when you are talking about creep of nanomaterials, and we will see in this case that in some systems we do expect what our expectations were, but in many other systems we not only do not see what our expectations were, but we can even see effects opposite to that what we had expected. So, if you talk about two important systems like nanocrystalline palladium and copper, which have been pretty well investigated, and you can clearly see in these cases the grain size is of the order of 40 or 20 nanometer, which is extremely small. In this system there seemed to be no increase in creep rate as compared to the micron sized counterparts. So, this is pretty startling, that we did expect that we would have increased creep rate when you go down to nano sizes, but there was no increased creep rate. Of course, when we are comparing and micron size grain, we are using the same temperature as for the comparisons. And more surprisingly, in some temperature regimes, even a lower creep rate was observed in the case of palladium. So, this is in direct contradiction of our expectations, which wherein we thought that there is going to be enhanced creep rate, and therefore, this is extremely surprising in the case of nanocrystalline materials and the creep behavior. Studies on copper in the grain, and here we are talking about a small distribution of grain size, which is 10 to 25 nanometer, and palladium about 35 to 55 nanometers, and here in the 40 nanometers can be thought of an average in the regime between 35 and 55. That means, again at the heart of the mechanisms, we have to keep in our mind that though there might be an average grain size reported in literature, but there is always a spread in grain sizes, and more the statistical data we get, we will actually find out what is the true distribution of grain size. And TM in these structures showed there is a porosity in the sample. That means, there was some damage, there was some and the question of course arises that was this damage accumulated during the testing time, or was it a effect of the prior porosity in the sample. So, this is an important question. I do not think the authors investigated that part. Creep in, and then the creep study was done in two temperature regimes, one in the low temperature regime of about 0.24 to 0.33 Tm, and one in the medium temperature regime, which is about 0.33 to about 0.5 Tm. And in this case, there was low creep rate and low grain growth. And in the case of the high temperature or medium temperature regime, the creep rate was decreasing even after a long testing time, and more importantly, there was grain growth. That means that if I have grain growth, I am essentially changing the microstructure of the sample. And here we are not talking about a small grain growth, we are talking about a grain growth wherein the grain size increased by a factor of 4 or more, and this we are talking about the average grain size, which implies that the microstructure is continuously changing. Maybe there is also porosity in the sample which is increasing, and therefore, it is difficult to characterize creep in many of the nanocrystalline materials, because I cannot understand if this decreased creep rate is occurring because of the nanocrystalline effect, or is it occurring because of the increase in grain size which is taking place during the testing. And therefore, these are very serious issues associated with creep testing in materials, that often we do see porosity, often we see a lot of grain growth, and therefore, it is difficult to separate out the effect which is coming purely from the nano size grains vis-a-vis the changing parameters, structural parameters, as the test is being conducted. Now, the below is shown, for instance, the studies on this copper material, which is has a grain size in the range of about 10 to 25 nanometers, and in this plot we have the instantaneous strain, which is the elastic strain, initially has been removed, and the initial creep regions of the curve also excluded in the plot. And if you observe this, there are, you see that at lower temperature, of course, the overall creep strain at a given temperature, suppose I take a temperature like a time for about 10 hours, in 10 hours at a lower temperature, of course, you accumulate lower strain, at a higher temperature you accumulate higher strain, which is what is expected, but additionally you notice that the creep strains are continuously building up even after long hours of testing. To summarize this slide, in copper the creep rates in the nanocrystalline sample was comparable to the micron sized grain size sample, but in palladium nanocrystalline sample, actually we could see certain lowered creep rate at certain temperature regimes. So, this was extremely surprising, as in the case of creep of nanomaterials. But this is, of course, as I pointed out, in the case of testing of nanocrystalline materials, even in cases where we are able to control the artifacts includes porosity in the initial sample, artifacts include grain growth, which you just talked about. Even when we are able to account for some of these effects, there is no universality. That means, in some cases you do observe a decreased creep rate, some cases you do not, you observe a similar creep rate to the microcrystalline counterparts, but there are other examples wherein the creep rate increased with the decrease in grain size in the nanoscale regime. That in this was an alloy of nickel and phosphorus. the creep rate of 30 nanometer grain size material was higher than the 250 nanometer grain size material. That means, by decreasing the grain size, and of course, both these grain size are in the nanoscale, one is 250 nanometers and one is 30 nanometers, there is an increase in the creep rate. So, we have seen that all three possibilities exist on reduction of the grain size. Of course, the comparisons are slightly different, because in the first case we had compared, in the case of copper, we had compared the nano grain sized with a micron grain size sample. Here we are comparing two nanometer grain size samples, and we see that there is actually an increase in creep rate as we decrease the grain size. In cases where high creep rate expected for nanocrystalline materials, like we see for palladium and copper, which are nice metallic materials where the diffusion rate is high, was not observed. The reasons are typically attributed to the presence of low angle grain boundaries and twin boundaries. And these low angle grain boundaries are, as you know, low energy configurations, and typically low angle grain boundaries by the Reed-Shockley model are decorated by these structural dislocations, which actually accommodate the misorientation. These are not prone to sliding and have a low diffusivity for vacancies. Therefore, because there is a predominance of these low angle grain boundaries, which is what is a theoretical basis for understanding that why such a material, in spite of being in the nanoscale, does not show high creep rate. And additionally, low dislocation activity is also being attributed to this low creep rate. We had seen that even when there is a grain boundary sliding, two other factors often come into the picture. One is dislocation activity, another is diffusion. So, because if you have just grain boundary sliding, you will have triple junction cracks, and these triple junction cracks have to be healed by diffusion and often have to be otherwise what we call healed out by plastic deformation, which involves dislocation activity. Therefore, to summarize these two slides on creep of nanomaterials, we have cases where there is an increase in creep rate on decreasing size. There are cases where there is not much difference to be talked about, but there are also cases where there is an increased creep rate on decreasing the grain size. And one nice example where actually an increased creep rate with decreasing grain size was seen is in nanocrystalline nickel, and these are room temperature studies. So, this is very, very interesting, because now we are this is something very close to the kind of expectation we had earlier raised, that we would have higher creep rate under two conditions, perhaps under higher strain rate and at lower temperatures. So, here the temperature is at room temperature, and of course, we are now making comparisons of grain sizes in the extremely small regime, in the grain size of the order of 6 nanometer, 20 nanometer and 40 nanometer. Now, if you see the plot of these three grain sizes, so you have the highest grain size, the 40 nanometer grain size here, and you have a decreasing grain size as you go from here to here. Now, what you note that this is a stress strain rate plot, and for a given stress and for a given testing time, you notice that actually the strain rate increased with decrease in grain size. The smaller grain size sample, the 6 nanometer sample, show a faster creep rate, and this behavior was attributed to grain boundary sliding, and which is of course accommodated by certain diffusion mechanism. But the high stresses and larger grain sizes, that means that if I go to the higher stress regime, and if I am talking about the larger grain sizes like the 20 nanometer or 40 nanometer samples, then dislocation creep seems to be the important mechanism. So, we can replace this 50 by 40, because this was the one which is originally involved in the study. So, this is a very nice example, the creep of nanocrystalline nickel at room temperature, wherein some of the initial expectations are actually fulfilled, and within this small grain size regime of about 60 to 40 nanometer, we are actually seeing a switch in the mechanism. The small grain size seems to be actually seem to some sort of undergo grain boundary sliding accommodated by diffusion, while the larger grain sizes under higher stresses seem to undergo dislocation creep. And we had noted some of these regions in the creep mechanism map, which we had seen earlier. So, in the creep mechanism map, we had noted that it is usually in the higher stress region, which is in this axis, that you tend to observe dislocation creep, and in the low stress region you tend to observe diffusional creep. So, you see that this is the region of the diffusional creep, and in higher stress region you actually obtain dislocation creep. So, this is a very interesting study. Again, we have to keep a few things in mind, that when you are talking about 6 nanometer grain size, we have to worry that obviously the grain size is not just one number like 6 nanometer, there is going to be a spread in the grain sizes, but nevertheless keeping all the other artifacts away, we notice that this is a very interesting example where increased creep rate has been observed at room temperature, and the creep mechanism is consistent with our expectation that it is going to be grain boundary sliding at low grain sizes, but nevertheless in spite of 40 and 20 nanometers being a small grain size, you see a switch in mechanism, especially when you apply higher stress. So, we have all kinds of material here. We have pure palladium, pure copper, we have alloys like nickel phosphorus nanocrystalline material, and we also have nickel. And you see that each one of these, though some of them are very similar like nickel and copper are FCC materials, we do see a very wide variety of behavior in the nanoscale materials. So, as far as the understanding goes today, that there is no what we may call generalized principle which we can apply to understand creep of nanomaterials, though we do understand some of the mechanisms which would be operated at larger grain sizes and the mechanisms which would be operative at smaller grain sizes. We had made a lot of observations regarding superplasticity in nanomaterials, and we had also noted previously that superplasticity in some sense is a very closely related phenomena to creep, except that in superplasticity damage accumulation does not lead to failure, and therefore you are able to get very long tensile elongations of the order of 350% to 2000%, and therefore this gives us a beautiful mechanism, or by superplastic deformation we can obtain nice shapes and we can use it as a nice production method. But in most cases it is observed that the initial expectations are again not fulfilled as far as superplasticity in nanomaterials is concerned. In many cases superplasticity is only observed in nanocrystalline samples where it is already observed in microcrystalline counterparts. That means there is nothing very surprising, and we have already seen that many cases we see a completely contradictory behavior in nanocrystalline materials as compared to bulk materials. And later on also we will see examples. For instance, there are materials which are antiferromagnetic in the bulk, but which will tend to become ferromagnetic in the nanoscale. So, these are very surprising effects, but in case of superplasticity most of the cases it is seen that superplasticity is only observed in cases where already in the micron scale grain size sample you observe superplasticity. Superplasticity was observed in nanocrystalline nickel with a grain size of about 20 nanometer at 0.360 m. That means it is more than about 450 degrees lower than the bulk material. So, having said that the initial expectations are not fulfilled, we will take up a few examples to see that where there is some interesting results. That means there are some examples where you did not observe superplasticity in the microcrystalline counterparts, but you did observe it in the nanocrystalline version, or you observed it at a higher strain rate, which is also very good, or you observed it at lower temperature. So, all three cases would be very, very interesting. So, maybe I should write this down. So, we will take up a few examples to see some of these what you might call interesting cases do exist when you are talking about superplasticity nanomaterials. And the first one is a case of nickel, wherein the 20 nanometer grain size sample superplasticity was observed more than 450 degrees lower than that for the micron grain sized or larger grain sized bulk counterpart. So, this is very, very interesting. In nanocrystalline Ni3Al, and you know Ni3Al is an intermetallic which has got a structure of Cp4, and the unit cell of a typical Ni3Al unit cell is shown here at the bottom of the graph. And when compared to the disordered alloy, you would notice that the Burgers vector is larger in this structure. Now, the fundamental lattice translation vector, because it is a primitive structure, is this, and if you had a disordered Ni3Al, it would have been this vector, which has a length of root 2 by 2, while in this case it root 2 by 2a, but in this case the Burgers vector has a magnitude of 100, and therefore the mod of the Burgers vector is equal to a. That means that the Pearl stress in such alloys, these ordered structures, is going to be large, and typically they would behave in a very brittle fashion and with very low tensile ductility at room temperature. So, if you observe superplasticity in these cases, it is actually very surprising, and the 50 nanometer grain size nanocrystalline Ni3Al became superplastic 450 degrees below its microcrystalline counterparts. So, this is again very beneficial. That means that Ni3Al is a technologically important intermetallic, and therefore, if I am able to superplastically form Ni3Al 450 degrees below its microcrystalline counterparts, then I have very important industrial applications for the nanocrystalline sample. Ni3Al had a ductility of 350% at 650 degrees at a strain rate of about 10 power minus 3 per second. So, here and again we are not talking about very high strain rates of deformation, reasonably what you might call slow strain rates of deformation, but nevertheless we have a good ductility of 350%, and given the fact that this intermetallic normally tension and tested in tension would have very negligible ductility, this is very good, and you can see the temperature is also very reasonable for an industrial application. So, therefore, we are able to see superplasticity at reduced temperature in a pure material like nickel, but also in an intermetallic like Ni3Al. In the case of 1420 aluminum alloy, showed superplasticity at high strain rate of about 10 power minus 1 per second. High amount of work hardening and higher flow stress for superplastic deformation as compared to the micron size sample is also observed in these cases. This implies that one of the at least the important expectations is fulfilled in the case of the 1420 aluminum alloy, wherein very high strain rates 10 power minus 1 is typically the almost like a normal tensile kind of a test strain rate, which you in a slow test you might want to perform, and therefore, this is not typically the regime of superplastic forming, like for instance 10 power minus 3 or 10 power minus 4. So, these are a couple of orders of magnitude higher than what you would usually employ in a superplastic deformation, and still you are able to obtain good deformation in the case of this aluminum alloy. The high amount of work hardening also implies that there is an accumulation of what you may call dislocation density, which is actually hardening the material. And here also you observe that the stress for superplastic forming is higher than its micron sized counterparts. Another interesting example is in the case of superplasticity in the 40 nanometer grain size zinc aluminum alloy, and this example is interesting because this alloy showed superplasticity about 373 Kelvin, which is a very low temperature, and strain rate is of course small, but the important thing here, the microcrystalline samples, that means the bulk counterparts of this, showed no superplasticity. So, this is another very interesting example, and now therefore, we have covered a gamut of all the possibilities. We have covered pure materials like nickel, we have covered intermetallics like Ni3Al, we have talked about alloys like zinc aluminum alloy and 1420 aluminum alloy. We have seen that superplasticity does take place in one of these cases at high strain rates. In couple of these cases, you observe superplasticity at what you might call much lower temperatures, and additionally you also observe superplasticity in cases where there is no superplasticity in the bulk counterpart. So, this is a very interesting gamut of possibilities when it comes to superplasticity of nanomaterials. So, we need to now worry about what are the mechanisms underlying this superplasticity and what are the issues which we need to address if we want to understand the results correctly. Superplasticity at low temperature, or equivalently of course, superplasticity at high strain rates at a given temperature in the superplastic regime is caused by increased diffusion, grain boundary sliding and dislocation activity. So, we have already seen that when you go down to nanocrystalline sizes, it is usually the grain boundary sliding mechanisms which becomes prominent, and this grain boundary sliding has to be accompanied by some diffusion and dislocation activity. So, this seems to be the overall picture regarding how the superplasticity is obtained in such kind of materials, nanocrystalline materials, at either high strain rates or at lower temperatures than what you expect for the microcrystalline counterparts. Like in the case of creep, grain growth seems a very serious issue during superplasticity experiments, and if grain growth is going to take place and if your expected superplasticity mechanism is grain boundary sliding, then obviously the elongations you are going to get is going to be limited purely because of grain growth issues. In the case of nanocrystalline nickel, it was seen that the grain size could increase to micron sizes starting from grain size order 20 nanometer. So, this is happening during the testing, that means during superplastic forming the grain size is increasing from about 20 nanometer to about something of the micron sized, which is a very serious issue in superplastic testing. That means that even though my initial material had this ability to deform to large extent, but during the test itself the grain growth would rather reduce my overall available ductility. In other materials the grain growth could be less. I mean, this was a very drastic example in the case of nanocrystalline nickel, but in other experiments it was not necessary that the same kind of grain growth was the issue, but nevertheless grain growth could have taken place. And you always expect that grain growth is going to be less in a two phase mixtures if the second phase especially is a precipitate, and or they are intermetallic compounds, because in intermetallic compounds, as you know, they are very hard, then and the grain boundary is less glissile. In two phase mixture the second phase has a pinning effect on the grain boundaries, while in intermetallics like NaR3Al the order has to be maintained as the grain growth has to take place, which means now that suppose I really want superplasticity retaining my grain growth, and my final product has to have the same grain size as my initial starting testing sample, that implies that I have to either work with a two phase mixture where the second phase could be a precipitate or a kind of a dispersion which will sort of impede my grain growth, which will have a pinning effect on the grain boundaries migration and therefore leading to grain growth, or I need to work with the intermetallic wherein the grain boundary migration involves also is impeded by the fact that now you have two sublattices or more, and for instance in the case of the Ni3Al, one sublattice is occupied by aluminum and the remaining three sublattices are occupied by nickel, and therefore this sublattice structure has to be maintained, and this means that grain boundary motion is going to be more difficult. In cases where grain boundary sliding is the predominant mechanism for superplasticity and one example for that is typically magnesium based alloys, it is seen that non-equilibrium grain boundaries give a lower elongation as compared to equilibrium grain boundaries, and this is expected due to the long range stress fields associated with non-equilibrium grain boundaries, which is expected to hamper grain boundary sliding. So, this is an important effect wherein we are talking about two kinds of grain boundaries, that grain boundary which is called an equilibrium grain boundary, but when we use the terminology equilibrium we have to remember that we are not talking about a global equilibrium, because in the global equilibrium case the system would not want to have a grain boundary and it would rather prefer to be a single crystal. What we mean by a equilibrium in this case is a local kind of an equilibrium, and what is implied by a non-equilibrium grain boundary is the fact that there are additional dislocations which are not the structural dislocations which reside close to the grain boundary. So, you have a grain boundary, and this grain boundary itself may be by the Reed-Shockley model may have certain dislocations which are now the interfacial dislocations, but or the grain boundary dislocations, but in addition to it this grain boundary may be associated with additional dislocations, and these additional dislocations which I am drawing in red give rise to a long range stress field for this grain boundary, because this array of dislocations does not have a long range stress field, while these red dislocations will give rise to a long range stress field, and due to these long range stress fields the associated with the non equilibrium grain boundaries is expected to hamper grain boundary sliding. So, this is issue which is wherein they have people have gone into details of the mechanisms of how the grain boundary sliding take place and what kind of a grain boundary would give you what you call an easy grain sliding versus a difficult sliding, and it is seen that equilibrium grain boundaries would slide easier as compared to the non-equilibrium grain boundaries which are associated with a long range stress field. In the case of Ni3Al, the high flow stress and extensive strain hardening during superplastic deformation has been attributed to depletion of dislocations and high stresses required for nucleation of new ones. So, we noticed when we talked about the Ni3Al structure and its superplastic forming here, and we noticed that you have superplastic deformation of 50 nanometer grain size sample. It is observed here that the high flow stress is observed, and additionally there is extensive strain hardening during superplastic deformation. That means with progress in superplastic deformation the stress has to be increased, that means the forming cannot take place at constant stress, and this is attributed to depletion of dislocations and high stresses required for nucleation of new ones. So, this is been the reason why Ni3Al is is difficult to form. But we have to also note the additional fact that Ni3Al being an ordered structure, the dislocation structures, the kind of partials we are talking, the kind of stacking faults we are talking is going to be very different from that of a normal material like aluminum. For instance, Ni3Al would have something known as superlattice intrinsic stacking faults and superlattice extrinsic stacking faults, which are not observed in the normal metallic counterparts. Next, we take up the important issue. We had a lot to say about a quantity known as the strain rate sensitivity. So, let us go back and review our slides wherein we had talked about this quantity called the strain rate sensitivity. We had said that we can do deformation at low temperatures or high temperatures, and when I mean low temperatures, we had said that temperatures below the recrystallization temperatures is about 0.5 Tm less than the 0.5 Tm or less. And we noted at low temperatures the important variable, the relevant variable amongst the 4 important variables stress, strain rate and temperature is strain. At high temperature, in another system, at low temperature system sort of becomes a build for energy, more and more dislocation densities tend to increase, and the system is a battery, and in other words, if you are spending X amount of energy, part of this energy is stored in the microstructure in the form of increased point defect density and dislocation density. So, it becomes a battery. At high temperatures, the microstructure continuously renews itself. That means, you have recrystallization recovery process taking place as the deformation is progressing, and this is typically called dynamic recrystallization, and therefore, the microstructure is constantly renewing itself, and therefore, the flow stress is not increasing with progressive deformation. So, here there is strain hardening, and therefore, you have an exponent known as the strain hardening exponent. At high temperatures, the relevant variable is strain rate and not strain, and of course, you would do all these tests to a constant strain at a constant temperature, and the important exponent here is a strain rate sensitivity. And of course, these two equations, the first one above and the second one which is relating, the first one relates stress strain and the second one relates stress strain rate, both are phenomenological equations typically found true for a certain broad class of materials and approximately true for the other kind of materials. Therefore, at high temperatures the strain rate sensitivity becomes an important parameter, and we had noted that when you have a high strain rate sensitivity, we typically expect superplastic behavior, and we had seen examples of this high strain rate sensitivity in superplastic deformation, and we had noted that in the case of superplasticity, the region with high strain rate sensitivity like between 0.4 and 0.67 is referred to as the superplastic regime in a log stress strain rate plot. So, this is where you get extensive superplastic deformation, and this is the region of high strain rate sensitivity. Now, we will say a few more things about this strain rate sensitivity, especially the difference in the behavior of strain rate sensitivity between FCC and BCC materials. So, how is that the strain rate sensitivity is going to change in nanocrystalline materials, especially as you change the grain size as shown in the plots below. First, I will go to the plots and we will come back to the text very soon. If I plot strain rate sensitivity as a function of grain size, and now I am in the nanoscale regime, and of course, I am plotting log of the grain size, you notice that for FCC nanocrystalline materials, the strain rate sensitivity decreases with an increasing grain size. While on the other hand, suppose I talk about nanocrystalline BCC material like iron, then I notice that the strain rate sensitivity actually increases with an increase in the grain size. So, the effects are exactly opponent when you are talking about nanocrystalline materials and the important parameter of strain rate sensitivity, and that implies that the behavior of strain rate sensitivity is drastically different between FCC and BCC materials. There is some understanding which we will see very soon, but the complete picture is not yet out. In FCC material, M decreases with grain size, and this grain size variation is over a few orders of magnitude, and in BCC material, M increases with grain size, unlike in the FCC materials. And you should be noted that the trend lines which we have seen below, so these are trend lines and these are not exactly followed for one material or one testing condition, are arrived by putting together results obtained in many materials, and these are obtained through many processing routes. And we have already seen the important differences and important property differences which can come from processing route itself. We had noticed that in the case of for instance, electro deposited nickel, how different in properties it can be from, for instance, a powder consolidated nickel. So, we have seen that processing route can play a very profound role, have a profound influence on the properties, and therefore, when we see such trend lines, we have to keep that at the back of the mind. In FCC materials, so far our understanding goes that forest dislocations, that means a single dislocation cutting through a forest of other dislocations, and grain boundary impediment seems to play an important role, and the exact reasons for this strain rate sensitivity are not yet clear. And so, we will not discuss that aspect more, but this forest dislocation hardening mechanism and also the grain boundary impediment mechanism seems to play an important role in FCC materials. In BCC materials on the other hand, mobility of screw dislocation seem to control the whole plasticity. Of course, this is true for any kind of BCC material, and this strain rate sensitivity dependence also seems to have a very profound connection with this mobility of screw dislocations in BCC materials. The reason being that in BCC materials, the edge component actually has a lower Pearl stress as compared to the screw component in any material, and in BCC materials the screw dislocation actually has a core splitting along the 111 plane in the 3 equivalent 111 kind of a direction, 3 perpendicular 3 directions which are 120 degree apart. As you know, in screw dislocation in BCC materials or in the Burgers vector is along the 111 direction and the screw dislocation actually splits, the core of the dislocation splits along 3 directions which are 120 degree apart. Now, of course, the this kind of a splitting implies that if the screw dislocation has to move, then the core has to collapse and move to a new plane, and this implies that the Pearl stress for motion of screw dislocations is very large. And therefore, if I am doing a plastic deformation of a sample having edge and screw dislocations, or more precisely having edge and screw components, the edge components would actually leave the crystal, which implies that I will be left with more of screw kind of components in the material. And this high Pearl stress implies that instead of the entire dislocation line moving, there is a mechanism which is, if you refer to the slide now, known as the kink pair formation mechanism. Its propagation seems to play a very important role. So, I will briefly draw what is meant by this kink pair formation mechanism and its propagation to understand plastic deformation in BCC materials, and also the case of which is directly connected or which is given as one of the important reasons for this strain rate sensitivity. So, if I have a dislocation line, the entire dislocation line can move by a Burgers vector and come here. An alternate possibility is that this dislocation line may actually develop a kink pair. That means, it can form a double kink like this, and then this double kink can actually propagate. That means, now the stress I need to apply is much smaller, because I am only propagating a small segment. I am not propagating the entire dislocation by one Burgers vector. So, this can actually propagate. And finally, of course, when the entire these segment would have left to the top, this segment comes down to the bottom, I would have the motion of a dislocation stepped up by 1b. Therefore, I can see that dislocation itself is a medium by which actually you can actually avoid the shearing of the entire crystal. You reduce that problem of shearing of the entire crystal to small regions in the crystal, and typically the analogy given is a fold in a carpet, that you actually make a fold in a carpet and roll it. So, pulling the entire carpet, I make a fold and roll down this fold down to actually get a little elongation, and I can make repeated folds to move the carpet. So, this is the analogy given to understand how a dislocation weakens a crystal, but this is a second order effect, wherein even this whole dislocation need not go by one single Burgers vector, but you can nucleate a kink pair, and this kink pair can propagate orthogonal to the direction of the motion of the dislocation, finally moving the dislocation. So, I can actually have a second order mechanism operating, which is going to weaken my crystal. But nevertheless, it is these trend lines we need to keep in mind, that we have exactly opposite trend lines when it comes to strain rate sensitivity of nanocrystalline materials, and this is, for instance, could be a material like BCC FCC copper, while this could be a material like FCC iron, BCC iron. Additionally, a few more points to be noted are that deformation in nanostructured materials seem to occur predominantly by dislocation at interfaces and not bulk deformation. You notice that, and this of course we are talking about very small grain sizes of the order of about 30 nanometers. We are not talking about the really large grain sizes where 100 nanometers and more, where actually you can have bulk dislocations. You can continue to have pileups, you can continue to have what you call Orowan and Orowan bowing and Frank Green mechanisms, but when you go to really small grain sizes, then dislocations at interfaces seem to play a very, very important role. And we have noted that an example here, that these are some of the interfacial dislocations, grain boundary dislocations, and additionally some of these which get closely associated, which creates my non-equilibrium grain boundaries. and if these dislocations sit exactly at the grain boundary, then they seem to have a Burgers vector smaller than the lattice dislocations, and in some in situ TM experiments mobile dislocation observed were not observed when the grain size is below 30 nanometer. That means really TM experiments have confirmed the fact that when you go into really small grain sizes like 20 nanometer and 30 nanometer, there seems to be a paucity of lattice dislocations, and it is the grain boundary region which becomes important from including from the sliding perspective and also from the perspective of dislocation activity. And in brittle materials like ceramics at small grain sizes, grain boundary sliding may be the predominant mechanisms for plastic deformation. So, this is already we have stated it before, we are just restating it, that grain boundary is the region of activity, and in brittle materials like ceramics typically there is not much of dislocation activity at low temperatures, and therefore, you expect that grain boundary sliding is going to be an important phenomenon. However, we have been repeatedly saying some of the aspects, and we just summarize this here, that much more work has to be done to understand creep superplasticity and also plastic deformation in general in nanocrystalline materials. We have already noted that in some cases the grain boundary structure is found to be similar to the bulk counterpart, some cases there is a difference between the grain boundary structure in a bulk versus the nano. So, what is the work which we need to be done, so that we can now put creep and superplasticity on a sound footing, wherein we can talk about a broader class of materials under one umbrella of or fewer parameters of understanding. In the case of creep, understanding rate control mechanism at various temperatures and strain rate needs to be understood. Creep tests need to be conducted over a wide range of temperature and stress, and the stress exponent and activation energy needs to be determined. Grain size sensitivity needs to be determined by synthesizing materials with a wide range of grain sizes. It is a very challenging problem, and not only when we are talking about wide range of grain sizes, we are talking about a close to mono disperse grain size. Large strain steady state creep experiment need to be performed, which is another area where a lot of work needs to be done. Pure materials should be used, because typically in multi-phase materials we have seen a few examples, though there is an advantage of using them because grain growth is small, but then understanding the underlying mechanisms become difficult in multi-phase materials. The role of triple junctions in creep also needs to be ascertained. That means that we already seen that triple lines and quadruple junctions are all very important in the case of nanomaterials, but their role is poorly understood when it comes to creep. In case of superplasticity, we need to obtain porosity free samples and surface scratch free samples, because surface scratches can severely limit the overall superplasticity which I am going to get. The role of grain boundary sliding in deformation needs to be determined, that how much part of it is actually grain boundary sliding, how much of it is actually plasticity or dislocation related mechanisms. Role of grain size on flow stress and mechanisms operative also need to be determined. So, though we have briefly listed some of the factors, it is also clear along with these we are to talk about additional effects, like for instance artifacts which can come from the samples, processing routes, and etc., which also always underlie when we are talking about some of these important effects which need to be deconvoluted. That means important effects which we need to understand, so that I can understand creep and superplasticity and also general plastic deformation of nanocrystalline materials. So, we will take up two case studies, two interesting examples of deformation of nanostructured materials or nanocrystals. In one example, the first example I talk about, what was done is that a carbon onion, if you look at the figure below, there is a carbon onion, that means there are multiple layers or graphitic like shells, inside which there is gold nanocrystal, or in an experiment conducted this could be gold or platinum nanocrystal which is enclosed within this cage. So, during the experiment what is done is that, so you have a gold which is a metal which is inside these graphitic or carbon onion shells. This is punctured by a focused electron beam, the shells are punctured, then this is extruded using this nano cage. Now, this is like a nano extrusion cell. So, you have a carbon onion which is punctured, and this gold actually is extruded like you would do a bulk extrusion from this carbon onion cage, and this extrusion has been studied. Now, if you go back to a very early experiment, going back to Ajayan, what he did was he took such an carbon onion shell, and without of course the gold inside, he put it under the electron beam of a 1.25 million volt electron microscope, and to his surprise he found that the core region of this carbon onion So, you have these nice carbon onion shells. So, this is a schematic. We found that the core region purely under the electron irradiation. So, he was using an electron microscope with 1.25 volt million volt electron microscope. So, inside these are the carbon onion, and this is, or more precisely, this carbon onion here, and this became diamond. In other words, under the electron irradiation and the intense pressure coming from these carbon shells, this interior of this carbon onion became diamond. So, this is a very interesting experiment which was published in Nature. So, you see that these carbon shells actually impose very high kind of compressive stress on the material inside. So, this is a later version of this experiment, wherein this high pressures has been used for the extrusion of gold. So, in this experiment what they do is that they take a carbon onion and then using these graphitic cages they extrude gold or platinum. The size of this nanocrystal is about 10 nanometer, which is present inside this, the blue color thing is about 10 nanometer, and this is a confined kind of a nanocrystal. The pressure experienced at about 300 degrees Celsius is of the order of 20 GPa. So, this is extremely high pressure, which is what this small carbon onion cage is able to impose on this gold or platinum nanocrystal. Given that the ideal shear strength of gold is only about 1 GPa, you see that this regime can be actually called the ultra strong regime, and therefore, you are actually extruding or keeping the material in the ultra strong condition under this kind of a carbon onion shell. The crystal had a perfect atomic structure with grain boundaries and stacking faults occasionally present. So, the gold crystal, when you observe it under electron microscope, occasionally you do see grain boundaries and stacking faults, but apart from that it is a perfect crystal, and because of this high pressure the lattice parameter is actually smaller than the bulk lattice parameter. When holes are punctured by an electron beam, the nanocrystal was extruded due to the high pressures inside the shell. And of course, the important question to ask, if there are no dislocations in the material, because you can see that there are grain boundaries and stacking fault, but there are no dislocations, then how is deformation proceeding in the absence of dislocations? Is it going to be dislocation diffusional mechanism like a creep, which is operative here, diffusional creep, or is it some other mechanisms? The mechanisms which the authors of this paper, which is Sun et al., they have proposed is that the mechanism is supposed to be because of nucleation and propagation of dislocations, though in their transmission electron microscopy observation they did not observe any dislocation, but they did molecular dynamic study and parallelly they performed diffusion calculations to show that diffusional effects could be actually smaller, but you do see that there is a faceting of the crystal when it comes out of the carbon nanotube, but this faceting cannot obviously take place without diffusion. So, that means diffusion is playing a role in the overall process, but they ruled out diffusion as a possible mechanism for this plastic deformation or the deformation of this gold nanocrystal through this graphitic punctured graphitic cage, and they propose that it is actually nucleation and propagation of partials or dislocations which is responsible for this kind of a plastic deformation in the ultra strong regime of crystals, wherein this material is kept under a pressure of about 20 gigapascals. So, this is one nice example wherein a nanocrystal is placed inside a nano cage which is extruded by a nano hole. So, this is a very nice kind of an experiment, and you can clearly see that the kind of pressures we are talking about, the kind of mechanisms we are talking about, the kind of experimental issues in actually observing some of the effects is very difficult, and we have to do secondary computations like molecular dynamics to actually sort of propose come up with a mechanism like this partials or full dislocations moving through the crystal and leading to this extrusion. In the second case is a case of deformation of silicon single crystals, and there are two examples we will take. One is the bulk silicon, wherein there is actually an indentation experiment, and there is also a compression experiment of silicon nanospheres, and we will try to see the difference in deformation behavior between bulk silicon and which is of course an indentation experiment, and the second experiment is compression of silicon nanospheres. In bulk silicon, which is typically called silicon 1, which has a diamond cubic structure, and we know it is a brittle material at room temperature. It actually transforms to a tetragonal structure under high pressure, which is what is experienced under a diamond indenter, and this structure which is tetragonal and which is a metallic form is called silicon 2. And this structure, the metallic form of silicon, is similar to the beta tin structure, and we know that tin also is found in alpha tin and beta tin form, and not only there is a crystal structure transformation when it goes to alpha to beta, but there is also a change in the character of the metallic character when alpha tin goes to beta tin. And this transformation in the case of silicon actually occurs at a very high pressure of about 12 GPa. And suppose I plot the load displacement curve for bulk silicon, and now this is load in indentation. This shows a very interesting feature, and if you look at the load displacement curve here below for bulk silicon, you see that during loading there is a nice smooth curve, but while unloading there are two important effects, that the curve comes and there is an additional effect which is called the elbow. That means there is actually a sort of a curvature change, and additionally there is an effect which is known as the push out or the PO effect, and this is observed only during unloading. Now, what is the reason for this? Is that this PO or kink back effects as sometimes called occurs during unloading and is a signature of the phase transformation of silicon 2 to other allotropic forms of silicon. So, you have silicon 1 which transforms to silicon 2 under high pressures, which is under the indenter, but when you actually unload, that means now you are relaxing the structure, this silicon 2 actually transforms to other allotropic forms like silicon 3 and which is BCC or rhombohedral silicon 12 structure, which are metastable forms of the silicon. And additionally, this elbow part which I mentioned is actually a signature of the amorphization of silicon. So, some part of the silicon is also getting amorphized. Now, if you compare this bulk silicon indentation experiment, which is a deformation experiment, with a deformation of silicon nanospheres. So, what I am doing here in the second case is actually I am taking silicon nanospheres and putting them under 2 and actually doing a compression experiment on silicon nanospheres. In that case, you observe that the loading part of the curve and also the unloading part actually shows a slight difference. In the loading part, you observe something known as a pop-in phenomena, and these nanospheres had a size of about 57 nanometer or smaller. So, but there was no pop out effect which we or push out effect which we had seen during in the bulk silicon. So, that part is of the curve is smooth, there is no PO effect when I am unloading the silicon. So, the difference comes in the nanosphere case is while loading, and this has been termed, this pop in effect, as a deconfinement effect, and it can be attributed to the onset of plasticity in a dislocation free crystal. So, clearly there is a very significant difference when you are trying to load bulk silicon in indentation vis-a-vis the compression of a nanosphere, and there are important effects which is technically called a deconfinement effect, wherein you are actually seeing the onset of plasticity in a dislocation free crystal. It should be noted in such experiments that the load is typically in the millinewton range and the displacement is in the nanometer scale. So, these are all very sensitive experiments done on silicon nanospheres with lot of care, and you do then actually try to see how a deformation of a nanosphere is different from that of bulk silicon, and you do see a difference when you actually do such an experiment, and the significant difference is in the loading stage of the curve.